So we've just finished walking up Slieve League there, and some beautiful views down here to the right. You can see the coast. So when I get home, I'm going to be talking about optimistic locking, and that's when you don't actually hold a lock before you modify the data. You're going to modify the data, and then at the end of the transaction, you're going to either update a version counter on the data, or you're going to update a timestamp flag, and that way, if that update on the version counter or timestamp was successful and you get a modification count of say 1 back, then you can go ahead and perform the commit on the transaction. Otherwise, you want to throw an exception, roll back everything you've done to make sure your data stays in sync, and then you can retry the transaction again and try and update the next value that was updated by the other transaction, and that way you can ensure that you're the only person modifying that data at any one time. So I hope you're enjoying the views here. I'll just swing you around. See that? So we just walked down here. So in this tutorial, I'm going to be walking you over a code base that I've just put together using Spring Boot and Java. And I'm going to show you how you can use optimistic locking in your code base to ensure that your data is not corrupt, that it's not stale, and that it is accurate. And you now have the ability to implement an optimistic locking concurrency control in your system. So why do you need this? So without locking in your application, if you allow one user, so one person using say a front end of an application, and they update an account, well, the result of that is that the data seems fine, the data looks correct, and everything worked. And that's because only one user modified a certain subject, so a certain account at that time. So there was no concurrent access. But if you introduce multiple users or multiple system feeds, so say you have an integrated application and you're receiving data, say in an MQ, well then this could produce unpredictable behavior if the different inbound feeds or people are modifying the same account. So this can produce corrupt data, strange behavior in a large system, as if a user in the front end is modifying an account and he sets the name to, he changes the name. Well, when they save that, they could see someone else's name, and why is that? So it can produce a really bad user experience in your system. And this typically is from an ostrich algorithm. So people don't know how their data is locking or how their concurrency control solution is in their system. So we definitely want to avoid this. And this typically occurs with the lost update problem. So this is a really good, nice example from Microsoft's TechNet. And that's really lost updates occur when 2 or more transactions select the same row and then update the row based on the value they originally selected. So in this context, you can see two users, so user Philip and user John. We both go ahead and select the same account. So we've loaded the account onto our front end screen. We then perform we then both update that account. So I change the name to Philip S and he changes it to Philip P. When we both press submit, well, one transaction is going to end up overriding the other transaction. So the last update overwrites updates made by the other transactions, which results in lost data. So the person who went last's value stays, but the person whose value went before is now lost. And why is that bad? Well, if you think of it this way, if user 1 and there's user 2, so we're going to step down. We both select the data at the same time. We both perform some calculation logic. And A is set to 3 in transaction 1, and A is set to 5 in transaction 2. And that is based on the value they selected, so 1 and 1. Well, transaction 1 then goes ahead and updates A, and then it holds write locks on that certain row, so that when user 2 now comes and updates it, it is now blocked until user A commits its transaction. So A now commits its transaction, sets it to 3. User 2, so the second thread comes along and says, okay, the write locks are now released. We then update it to update A. So now it's set to 5. 3 is now gone. While what should have happened is when this got set to 3, user 2 should have been notified or should have said, okay, no, there's been an update received on that data, and it happened between our commit and when we loaded data. So we need to roll back, we need to reload that data out of the database, perform our calculation to get logic again, and then commit the data. As if transaction 2 loaded the value A to be 3, it might not be set it to 15, it might not be set to 5, it might be setting it to 15 or some other value. So this needs to roll back and reselect the data and to ensure that it has the right data, which would be 3 at this time before it performed its commit. So this is how you end up with dirty, inconsistent data. And I'm going to show you an example here how you can prevent that. So the first thing I had to do for this tutorial was go ahead and create a MySQL instance, and I created a schema called YouTube and a table called account table. And this is going to hold our accounts for this demo application. And as you can see, I've inserted one row and it's got a name, account ID, and a version. So this is the data we want to change. The ID is internal to the system. That's going to uniquely identify a row in this data in this table, and the version is to allow us to identify concurrent updates and ensure that our data is in sync and that no users are performing lost updates on the data. So in our code base, what I've done is went ahead and created a Spring Boot application that has one account controller. And the first thing I've done here is actually went ahead and loaded an account up. So this may actually be performed before you perform the update or the processing of your account. Because say maybe the user selects load account, you go to your database, you load the values, and you return that to the user's user interface. Well, if that's the case, you want to make sure that the user does not have access to change the version column, because it's going to be a very important column. So maybe you want to use some way of identifying that the version does not change between them HTTP requests. You may use a flash map or some other way of identifying that. So what we're doing is, we're passing the account ID in through the path variable. We're loading that up. And at this point, you would perform some calculation on the data based on what you had selected. And then we're going ahead and saying account service.save. So this is where we're going to perform our actual business logic and processing up and updating of our data. So if we go into the account service class, you'll see that it's marked as @transactional. So that means we're going to span a transaction with propagation required. And based on that, we're going to be able to hold write locks until this transaction commits on any rows that we write to. So what we'd actually do is we call into account DAO and call update. So if I go in the account DAO, I'll actually run over select first. So I'm selecting by the account ID. So if you remember in the controller, we select by account ID. Well, in this, what I'm doing is passing in the account ID, where then the account ID is getting mapped and saying where account ID equals account ID. We then pass in the singleton map, and what it'll do is return our unique row, because we have, of course, we have our index on that account ID column, and then mapping the account in based on the values returned, and I'm returning the account back to the client or back to the service there. The update, what I'm doing is performing an update on the account. I'm setting the name and the version to the version +1. So that's very, very important. That's the most important piece of the puzzle here. And we're only performing that version, and we're setting it to +1 where the version is equal to the version we have selected and the account ID equals the account ID. And that's getting mapped using the bean property SQL parameter source. So that's going to map based on our account variables inside this class. So of course here you see account ID and account version. Well, if we go inside account, you'll see that the names match up and they'll get substituted for us. So you can check all that out on the NamedParameterJdbcTemplate Spring documentation. I will post that below this tutorial. So back to the point, what we're doing is selecting that by, we're going ahead and calling into the account service, performing the update. And then what we're doing is saying if the updated account is not equal to 1, then we're going to throw an illegal state exception and say the data is stale and please retry that. So if you can imagine, two transactions come ahead and they both load the value from the database. So both of them perform the select. They both get version 4 back. Well, they'll both come in here. They'll both span a transaction each. They'll both go in the account DIO. The first one will perform its update, and it's going to say update account table. Set this where version, set the version +1 where version equals version. Well, the first one to perform that write is going to hold the write locks on that row. So no other transaction is going to be allowed to write to that row until the first transaction commits. And it's going to commit once it returns from line 27 there. So one transaction's processing and one's now blocked. So when the first transaction then goes ahead and says, okay, we update that to 1, and as part of that update count, it set the version now to +1, which would actually be 5. And then when the second transaction performs its update, it's going to say where version equals version +1, and remember it's still on 4, so it's going to set it to 5, where version equals 4, but version is now 5 from the previous transaction, so that's going to have an update count of 0. So now we have an update count of 0, and that's not equal to 1, so that's going to throw an illegal state exception saying data is stale, please retry. And that's one simple way of identifying a concurrency issue or using optimistic locking to stop concurrent modification to one subject or a certain data. So I'm going to run that. I'm going to put some breakpoints here in the threads, and I'll actually show you maybe some Spring Boot code as well on how it actually gets wired together. So the first thing I'll show you is how it gets wired together. So if we go in our Spring dependencies here, and I'm going to load up the JDBC auto configuration. If we go into DataSourceTransactionManager auto configuration, well, down in here we do not have DataSourceTransactionManager, and it's going to identify that. So we have the classes, and we do not have a platform transaction manager, and the data source transaction manager extends the platform transaction manager, as I remember. So abstract platform transaction manager implements it, and that's going to be true. So we're going to now have a data source transaction manager managing our data source. Now also the data source is going to be injected into JDBCTemplate, actually not a JDBC template, a NamedParameterJdbcTemplate. So the same data source is going to go in here, and that's actually going to have a JDBC template inside it. And if you want to get access to that, you can call classic JDBC template. I think that's so we search return this dot. So if you want to get access to the JDBC template, you can call it get JDBC operations if you really want it. So that's how our data source gets wired together with our JDBC template and our transaction manager. And that's cool. So now we're ready to perform our transactions. So I'm going to go ahead and run this in debug mode, and I'm going to go ahead and load up Google Chrome and submit a couple of requests. So there are applications starting. I'll go in debug mode here. I'll play that through. Let everything run. Okay, so now we have our application started. We do not have any active HTTP requests. And what I'm going to do is bring in Google Chrome here. And I'm going to submit a request. 2 requests actually, so there's 1. So here you can see 1 thread spawned. There's 1 request. And number 2 comes in as well. So now we have 2. See here? 2 daemon threads running. So with the first thread, we're going to switch between them. We're going to go here, and what we're going to do is load up the data. So it's going to go ahead and say, okay, we've got an account. So Philip 123 version 4. Let's minimize that. Go into the second thread. We're going to load the account as well. So now we've got the same account, Philip 1234. And remember, these are 2 different users modifying the same data at the same time. So you can envision 2 people, 2 different computers modifying the same data in 2 different UIs. So there we're going to load the account. We're going to switch back to the other thread. It's going to load the account. So here you can see, oh, I've misprinted that. And what we're going to do is go ahead and keep on going. I'm not going to go and change my logger for that. And what I'm going to do is go into the account service.save. And you'll see here it's now, I have a breakpoint in my update. Well, if I switch back to the other one, I'm going to say account service.save. I'm going to make sure I have a breakpoint in my update count here. And as you can see, I'm going to perform the save there as well. So now there's 2 threads on the same line. And remember, one's got 4 and the other's got 4 as well. Well, if we go to thread 2 and let's say it performs the update first, so there, it's performed the update. I'm going to allow it to play. Well then, if we go into the other thread that hasn't performed the update, you'll notice that it'll now block. So see the thread, it's gone, it's blocked. So it's actually blocked on the update because this thread now owns the write locks of that table, because we're in a transaction. So everything in here is one atomic transaction. So that allows us to update multiple tables within one transaction, ensure everything stays in sync. So we have no choice but to allow this guy to actually go ahead and say, okay, update count is not equal to 1. Well, it is equal to 1. So it's going to go ahead and play. And once I play this through, you'll see the next transaction will then unblock and be blocked and be released here. So I play that through. Okay, so now the thread that we played through is now gone. And if we go to Google Chrome, the first one is completed. And the second thread, you'll see here that if we step over, its update account was 0. And that's because the last transaction had updated it to 5. And the query was based on 4 because the account selected is 4. So we have an update account of 0 in the data. We can view that data in our database. We won't be able to view it because the write locks are still in the account. So it's going to spin. Oh, sorry, it's not. You're going to see version 5 there. Because no one holds the write locks anymore. And you'll see now what we can do is say, okay, version is not equal to 1. And based on that, we can say, okay, please retry. So that way, we've performed optimistic locking and we've said, okay, 2 users are modifying the same data. Let's find some way of identifying that. And using a version column or some kind of timestamp is one way of building that in. So that's one simple way of using optimistic locking, or it's one idea. Maybe you can implement something different, or maybe you can use JPA, or Hibernate has a lot of this stuff built in already. But I just wanted to go over some concepts about that. So we go ahead and play that through. You'll see that we got an exception here in the data, which is the data stale. And you can throw this back to your UI and you could say, okay, reload the data. It's going to click reload and it's going to load the first thread's values that it changed on that account. So I hope you guys enjoyed this tutorial. I hope it made sense. I love looking at all this stuff. So this is optimistic locking, and I should probably say, you want to use optimistic locking if you have a low chance of collision within your data. So if you have a high chance of collision, meaning that you're pretty sure that people are going to collide all the time, you maybe want to consider pessimistic locking. So you're going to hold a lock up front in your data, and that's even before you change it. So you say, I'm going to change this, I'm going to hold a lock, and then you release the lock when you're complete. So you can do that based on transaction isolation levels, or you could do it based on, you could have maybe a database table, and when you insert a row, you have a primary key on certain columns. So when other people try to modify the same data, it gets a duplicate key exception, or a basic standard mutex table to perform. You hold a write lock and then you select from another transaction table and see what's in there. So there's lots of ways to do this. But I like optimistic locking. You don't perform the lock up front, you hold it right to the end, and it typically works very well in most cases. So subscribe to more tutorials. If you enjoyed this, give it a thumbs up, give me a like. You can write to me on Twitter, Philip Starrett, and I look forward to making the next tutorial. So okay guys, see you later.